Okay, so let's get started. Are there any questions about anything? So I presume that all of you have looked at your um, exams, right? So you're able to see all the details, right? So you're able to see the questions, the answers, everything, right? Okay, good. So
Oh, Professor, just a quick question about the 10 points.
yeah,
Does that get added to the, because it's out of 113, is it added to the
so
overall score?
the because of how to keep track of things, it's just going to appear as part of your practice test, right? So when we add up, it's that's going to be taken care of in the total, right?
All right.
So but we are not going to add that specifically to the midterm. We're just going to leave the midterm the way it is because it's not easy to do that.
All right. Thank you, Professor.
Yeah, the result is the same. uh don't know what you mean by it's curved. So it's the number that you get, right? So it's the points are assigned to your each problem, which I think you see in when you look at your results. And so it's going to show you how many points you got. And uh, I don't there is no such thing formally as curving that we do, and I don't think you'll see that in any courses you take in the department. There may be a few exceptions, but mostly no such formal curving is done. What we tend to do is, of course, the way the exams are designed, sometimes they turn out to be harder, sometimes they are turn out to be easier. So the average in the class definitely is a factor that goes into how the grades are finally assigned, right? But there is not a uh, you know specific curve that we use, distribution that I'm going to look for, or any such thing, right? So again, there is no reason to if everybody is doing well in the class, of course everybody can get a good grade, right? So so there are no specific targets in terms of we'll only give out certain number of certain grades, right? But obviously the grades should have some meaning. uh, we obviously want you to learn the material, and you know but if you have learned the material sufficiently well, then you should get a good grade. So that's all I can say. And something more uh, concrete we can have, I can give you more concrete information when we get through the next midterm, right? So then closer to half of your grade, half of the total number of points in the course should be finalized by then. So then it would make a lot more sense for me to project something. Okay, so let's pick up from where we left off last Tuesday. So what I'm going to do today is today's class is going to be like a mix of a recitation and lecture. So we are going to see several problems mixed in with the lecture material, um, and then towards the end of the class, we will have primarily problems. Okay, and so we'll take a break somewhere in the next hour and 10 minutes, and then continue the recitation just like we did last Tuesday. Are there any other questions? Okay, so we are in the midst of the counting topic, right? So and before counting, we were discussing um, summations, right? Summations and series. So your next homework is going to be on these two topics, right? Series and summations, and counting. And it'll probably be distributed tomorrow maybe, right? And then you'll have some time, maybe 10 days to return it. So I need to sort of work the schedule um, for the next midterm, right? So the date of the next midterm we have set up, but before the midterm you have to have the homeworks, and then we have to have time between the homeworks and to prepare for the midterm. So I have to sort of calculate all of that, and then I will set the deadline. But certainly the homework is coming out in the next day or two. Okay, so in the last Tuesday we looked at several ways for counting, several rules for counting. There is the product rule, which says that if you have you know if you have P1 ways of doing one thing and P2 ways of doing another, and up to Pn ways of doing the nth thing, and all these things choices are independent of each other, then the total number of combinations is obtained by simply multiplying the number of ways you can do each of these things, right? So this is very familiar, pretty much the first rule that you learn when you learn about counting or probability, right? So in the case of probability, we talk about multiplying probabilities when you talk about two things happening together. In the case of counting, we multiply the number of ways of doing each of these things. Okay, and then you have the sum rule, which says that if if you have a number of disjoint sets, then the total elements across those sets can be obtained by simply adding up the elements, right? So when stated in this form, it's of course, sounds almost trivial, right? And so basically we apply it when we have, n different ways to do something, and each of those ways, can be, each of those ways can be further subdivided into P1 ways, P2 ways, and up to Pn ways. And then if you want the total number of ways in which it can be done, then you simply add up this, right? And then we talked about generalized product rule, where there are additional conditions. For instance, the specific condition here is that if you are going to hand out awards for, if you're going to hand out M awards, then the same person cannot get more than one award. And when you do that, then that limits your choices for subsequent awards. The first award can be given to any of the N people, but the second award, the person who just won the award is no longer eligible. So there are only N-1 choices for the second award, N-2 for the third award, and all the way to N minus, these are all should be M here, right? So N-M, and so this is something that when you learn about permutations in school, this is a formula that comes up, okay? And we use that to look at solve this problem of how often do repetitions occur in numbers, right? Then the third rule we talked about is division rule, which basically says that if if you create arrangements, and some of these arrangements are indistinguishable, then you need to sort of count, divide up the arrangements by a certain number in order to get the really unique number of arrangements. And we used an example of arranging pieces on the chessboard, and we looked at essentially, first we counted the number of ways to arrange, uh, uh, you know, two identical rooks without worrying about the possibility that we could be counting something more than once. And that gives us this number, because the first rook can be placed in any row and any column, and that gives you 8 rows and 8 columns as the possibility. And for the second rook, we have to choose a different row and column, because that's the condition here, right? So you need to take 2 rooks and put them, arrange them so that they occupy different rows and different columns. Therefore, for the second rook, you have only 7 possible rows and 7 possible columns. And so that leaves us 31, 36 possibilities. But now these are 2 identical rooks. So what that means is that this position and this position will be indistinguishable, because all you have done is that you have taken 2 identical rooks and switched their position. And because they're identical, you can't tell that any such switching has taken place. And so what you need to do is you need to apply this division rule, uh, saying that these 2 positions cannot be distinguished. So whatever I counted here, I need to divide that by 2 in order to get the unique number of arrangements, right? So counting is always tricky, because we make mistakes in checking whether, when we apply the product rule, we sometimes miss the fact that the choices are not independent, right? So we think they're independent, and then we multiply. Well, it turns out to be wrong. And secondly, if we have if you're talking about addition rule, then there is a condition that the sets be disjoint. And again, sometimes we miss the possibility that we are counting sets which do have some overlap, right? And then in the case of division rule, we often fail to apply the division rule, right? We think that the arrangements we are considering are all distinct and distinguishable, but many times they are not. And therefore, you end up having this making mistakes. And so one thing you should remember is that everybody makes mistakes with counting. We all want to get better at counting, but we will all make mistakes all the time. And so when I give you solutions, or when I discuss problems in class, watch out. And then when you find a mistake, point out, because this is something that happens all the time, right? That shouldn't prevent us from counting, but just be more vigilant, and get the and realize where we are going wrong. Okay. Okay, so to illustrate the division rule, we looked at knights around a circular table, and the point there is that if they are sitting in a circular table, if everybody shifts around by 1 position, then you can't tell the difference, right? So which means that if there are m positions, there are going to be m such shifts, all of which are going to yield the same arrangement if you simply look at the neighbors of everybody, right? So as such, in this case, we need to divide by okay, another typo, right? So that must be m, right? This was a question last time when we were discussing that somebody said n instead of m, right? So there are m seats, right? So then there are only m possible shifts, all of which are going to result in the same situation. Okay. Then we looked at combinations, right? So if which is also another way of thinking about it is to think about subsets, right? So how many 5-card poker hands can be dealt from a 52-card deck? So we are talking about a 5-element subset from a 52-element set, right? So how many distinct 5-element sets are there? And the way this is a very well-known problem, and I'm sure most of you know how to do this. And the formula is, we have a special notation for that. It's just called, n choose m. Sometimes this is called a binomial coefficient. But basically, it represents the number of ways to choose an element, choose a subset of m elements given a set of n elements, right? So that's why it's called n choose m, okay? And then we went through our donut example, and the very last thing we did was to count the number of binary strings with exactly k1s. This problem itself is very simple to solve because you are simply choosing the, which of the k positions among the n bits are going to be ones, right? So essentially it's a subset, right? So the original set has n elements corresponding to n positions in the binary string, and you want to find out which k of these, right, or which subset of k positions should have a 1, right? And once you make that decision, then you have an exact, you have completely specified all the possible binary sequences with exactly k1s, right? So the recurring theme in counting is bijection, right? So remember when we were talking about cardinality of sets, we were using bijections to prove that sets have the same cardinality. And when you deal with finite sets, counting is still going to be based on bijection. And sometimes we don't realize consciously that we are constructing a bijection in order to count. But there are going to be other problems where you need to explicitly think about bijections because it's hard to count in the original problem. But then if you map it into a different problem, and then in the new problem, you're able to count very easily. And then, to make sure that your count is right, the original set, right? So you start with the original set S, let's say S1, and then you find it, S1 somehow you find it is hard to count, right? And it may be our mental, limitation, or something else, or it could be some other reason. So what we will try to do is to define another set S that is somehow easy to count. Right? And then, of course, we can go ahead and do the counting here. But obviously, we need to make sure that this count that we make here is going to be match exactly the count that we have here. And the basis of that is going to be showing that there exists a bijection from S1 to S2, right? And this is one of the first examples where we are going to see this, play out, okay, in this, donut example, right? So, so remember what we are. So let's go through the problem again. So we have the donut problem. Now, the donut shop is making 10 different types of donuts, and the shop sells you boxes of dozen, right? And the chef there wants to make sure that everybody gets a unique box, right? So no two boxes are identical, right? So you're asked to count, given, 10 different donut types, you want to fill a 12, a box of 12, and how many ways are there to do this, right? So you can think about how to do this, and if you think about it, you'll realize that it's not obvious how to do this counting, right? Because you can say, hey, how many donut types am I going to have, right? So then you can say, I could have, one way to do this is to say, okay, I could have 10 donuts, or rather, I could have, 10 different types, right? Or I could have 9 different types of donuts in the box, 8 different types, all the way up to just one type, right? And then I can say, if there are 10 types, then I need to decide of these 10 types, which one am I going to have, uh, 9 times 1 plus, 1 times 3, which means that you have 9 types of donuts, each, one of each, right? And then the last type, you have 3 donuts, right? So this is one possibility. And then the next possibility is 8 times 1 plus 2 times 2. And I guess that's it, right? So those are the two ways in which you can do this. And now you can, so the point is that if you think about it in the most obvious way, you need to consider, so many different cases, and you can see that it will take you forever to calculate it if you think about it this way, right? So this is why we think of a different way of thinking about the problem, which is that we map it into this problem of you know binary strings, right? And the way we think about it is that, okay, so let's say we have 12 donuts, right? So 12 donuts. So we're going to represent these 12 donuts by using 12 zeros. And then we are going to use the ones to tell us when to switch from one type of donut to another type of donut, right? So if you have something like this, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0. Okay, how many types do we have? So what this thing says is, choose, one of the first donut type, one of the second donut type, and so on. The fourth type, you're going to pick 2. Fifth, sixth, you're going to pick 1 each. Seventh, you're going to pick 2, and so on, right? You could also have something that says, which says pick 12 donuts of the first type and pick 0 of every other type, right? So the way to interpret this number is that you have the 10 types of donuts in front of you. When you see a 0, you pick from the current, you start from the first type. When you see a 0, you take a donut and put it into the box. When you see a 1, then you move from the current type to the next type, right? So this way you mechanically think of this string as representing an algorithm for, that tells you exactly how to fill this box, right? So, and then you can say whether each such string tells you, exactly one way of filling the box, right? And that is the bijection you are trying to establish, right? So you want to say that every possible, filling of a donut, filling of the dozen, can be represented by one such string, right? And exactly one such string. And you also want to show that every such string represents exactly one way of filling the box, right? So this is how you show that there is a bijection between the ways of filling the donut box and these binary strings containing 9 ones, right? And 12 zeros. And each of those binary strings with 9 zeros, 9 ones and 12 zeros, there is a unique correspondence between them and the ways of filling the donut boxes. And therefore, we can simply count these binary strings, which we already know how to do, right? So there are 21 positions because there are 9 ones and 12 zeros. So there are 21 positions, of which we have to choose 9 of them to be ones. And so this ends up being a 21 choose 9 problem. And so in all of these counting problems, I'll typically show the final number as a numeric quantity, but that's not really what is important, right? So what is important is the formulas and the method that we use, right? So when you have your homework or in an exam, don't try to just say what the final number is, because we will not be able to give you much credit for a number, right? And most of the time, again, the number may be off by a little bit, and we can't tell whether off by a little bit is because you made a small mistake or you made a blunder in how you calculate it. So in counting problems, we are always interested in seeing the formulas and expressions, and not, so this is not what we are looking for, right? So this is what we are looking for, and an explanation why the way that you're using for counting is actually correct, right? So this is really important. Okay, so can I see more of you so I have a little bit of a better idea where people are? Okay, so so let's say we had a requirement that there be at least one donut of each type, right? So how can we solve the problem now? Can someone tell me? Again, there are 5 times the number of people that I see in the class, so I'm sure more of you can switch on your cameras for my sake. So again, we are talking about the same problem, but we added a requirement that you have to choose at least one donut of each type, right? So how can we solve the problem now? How can we do this counting now? Somebody wants to try? Again, remember, we are always going to make mistakes, so there's no need to sort of feel bad that you're going to make a mistake, because everybody is going to make mistakes, right? So that's just how it is.
Well,
And, yeah, go ahead, please.
well, if you have to have one donut of each type, wouldn't then the ty- then I'm not sure. I'm not sure what the equation would look like, but then you'd
Yeah.
have to. It'd be something with a factorial because you'd have to reduce the options you have each time you multiply, right?
Right. So the point about many of these questions is that we want to try to simplify the problem in some way, because just like I was trying to do this the long way, the long way is sometimes just too long and we'll never complete the problem, and other times the long way may be just wrong. So in this case, the long way may be right, but again, we may need, it may be difficult. Frederick?
Well, if you have to have one of each type of donut,
Right.
then you have to, that already takes up 10 different donuts.
Right.
So you just have 2 spots left to fill. So it would be 12 choose 2.
12 choose 2.
Or sorry, 10 choose 2.
Right.
10.
Okay. So it's not exactly 10 choose. Is it 10 choose 2? But the first part of your reasoning is right. So if you have to have one of each type, we might as well simplify the problem by, satisfying that condition, right? And then saying that we only have a choice of the remaining 2, right? So the remaining 2, we are going to decide whether it's going to be, donut type 1 or, 2 or whatever, right? So now
It's not.
yeah, go ahead.
I was going to say something, then I realized it's completely wrong.
Sometimes we do learn a lot from the mistakes, because again, this is tricky, right? So we will over time you get better, right? So that's the goal, and that's the hope. So so again, all you need to do is to count the ways to choose the other 2, right? And therefore, if you we can, of course, just apply the technique that we already know how to fill, 2 slots with 10 quantities, and therefore we end up with 55 ways, right? So the answer you gave me was 10 choose 2, right? But that does not consider all the possibilities, because 10 choose 2, what it says is, again, you're choosing a subset of 2 from a set of 10. And because it's a subset, nothing can be repeated, right? So you are putting this inherent, implicit condition that, the 2 types that you choose are distinct types, right? Which is not needed, right? So you can choose, both of them could be the same type, right? And that additional possibility is, what is reflected here, right? So basically, if you do 10 choose 2, right? So that'll give you 45, right? This is 10 times 9 by 2. So that is 45, right? And these 45 consist of the choices where the 2 slots are filled with different types of donuts, right? Now you have 10 additional choices where you choose the same donut for both slots, right? So you add that 10, and then you get the 55 that we get here, right? So what this shows you is that there are multiple ways to count, right? And we want to find one of the simpler ways to count, but often it's not the only simple way. And then, but obviously, if we are doing the problem right, then whichever way we count, we should end up with the same answer, right? And in fact, this is sort of the only way we have for checking ourselves, right? Because hopefully we think about the problem in one way and that yields one answer, and we think about the problem in a different way that yields another answer. If the two match up, then we have more confidence that our method of counting is right. Right, so that's what is summarized here. There are two ways of counting, and then once again, the number is 55. Okay, right, and there are multiple ways of counting, and you want to check, right? And when you have a problem in the homework or in the exam, this is the technique you should use to verify your logic, right? Of course, sometimes you won't have the time. Well, then you have to move on. But when you have time, then try to think about the problem in more than one way and verify that, in fact, you get the same answer. So, so we were talking about the n choose m problem, where you start with a set of size n, and you want to choose a subset of size m. And we said, okay, so there are n choose m ways of doing that. Okay, so but what if you don't want to just one subset, but you want multiple subsets, a1 through am, such that these subsets together cover the whole set? Okay, so we want to split a given set into m subsets, right? So the word split says that every element should appear in one of these and exactly one of these, right? So so we want to find out how many ways, we can do this, right? So so we can use the same kind of reasoning that we did before. So we take a permutation, which is essentially a way of writing down all the elements in the set in some order, right? Right. So a permutation of a set is a way of arranging the elements of the set in some sequence, right? And how many, given a set of size n, there are n factorial permutations, right? Because we can fill the first position with one of n elements, the second position with one of the remaining n minus 1 elements, and so on. So if we just think about the number of ways of number of permutations of the elements in a set, that's always going to be n factorial, right? And then we can take these, let's say we write them down in element 1, element 2. Then we can say the first k1 elements, we are going to call this as the set A1. And then the next k2 elements, we are going to call this as A2, and all the way to the last km elements are going to be called AM, right? So this is how we can take any permutation and simply interpret that as specifying one choice of these sets. Okay, so so this is telling us how to do the split. But then, if let's say, for example, let's say k1 happens to be 2, right? So we would be E1 and E2 will not be different from E2 and E1, because both of them represent the set, right? So for that reason, what we need to do is, although each permutation can be thought of as representing one of these sets, if we do that, then we will be counting cases like this where all we have is a set A1 with elements in different orders. So we have to apply the division rule to eliminate the duplicates. And when we do that, we end up with this formula which says that, okay, I'm going to start with all of the permutations of the original set. And then I'm going to read off the first K1 elements as A1, next K2 as A2, and so on. But then to eliminate the duplicates or eliminate the multiple ways in which A1 could be specified, we know that A1 contains K1 elements. So its elements have K1 factorial permutations. So all of these K1 factorial permutations, we are counting as if it's a different instance of the set A1. Therefore, we have to apply the division rule to divide the original number n factorial by K1 factorial to eliminate those duplicates. And once again, for A2, we have to divide by K2 factorial to eliminate the duplicates, all the way to divide by Km factorial to eliminate all the duplicates of Am, right? So, so this is this expression is represented using a variation of the choice notation, and it's called a multinomial coefficient, right? So far we have been using this n choose m, which we said is called the binomial coefficient. This one, which talks about taking a set of element n and dividing it into m subsets with specified sizes. That number, right? The ways of splitting a size of a set of size n into m subsets with specified sizes, that is called a multinomial coefficient. Okay, so the naming is not important, but you can sort of remember that this notation. But most importantly, this particular formula that says how to solve this problem. Okay. So again, what we are going to do is that the same set of 3 or 4 rules are going to be applied again and again, and the trick is always to make sure that we we aren't making mistakes. Okay, so let's look at a slightly different problem. Okay, so how many ways are there for permuting the letters in the word bookkeeper? Okay, so bookkeeper has 10 letters, right? So how many permutations exist of these 10 letters? So can someone tell me how we might approach this problem?
Would it be 10 factorial?
So
well, are we allowing like two, since there's 2 O's, are we allowing both O's to be used, or?
of course you're allowing both O's to be used.
Okay.
But so this is not, if you flip these 2 O's, right? That's not a different permutation, right?
So the K and the E.
Would you have to divide by like 2 factorial for the 2 O's,
right?
2 factorials for the 2K, and
Right.
3 factorials for the 3 factorials for the 3 E's?
Correct. That's exactly what we need to do, because once again, we start with the permutation, things look okay, but then we realize that in the permutation, we are counting some things multiple times because we can't really distinguish between when those elements are switched around, we can't tell the difference. So when the two O's are switched around, we can't tell the difference, which means that each time we see an arrangement which contains, O in two places, let's not specify what else is anywhere else. So this exact sequence is going to be occurring twice if we look at the 10 factorial permutations. This is going to be occurring twice because the 10 factorial thinks as if this O is different from that O, right? So because of that, we have to divide it by 2 factorial and so on. And finally, so we need to, so there are only 3 letters that are being repeated. O is repeated twice, K is repeated twice, and E is repeated 3 times, right? So we need to divide it by, we need to eliminate the duplicates, 3 factorial for the rearrangement of the E's, 2 factorial for the rearrangement of K's, and the 2 factorial for the rearrangement of O's. And we divide by that, and then we'll get the final number, right? So once again, I always calculate the final number, but that's not important in the end, right? So any questions? So going forward from here, there are going to be a lot of problems that we are going to be solving, and it's important that you sort of stop me and get your questions answered, or else this problem solving is not that useful, right? Because obviously you need to be following this. We are more or less there are still a few more things that we need to that we want to discuss, but from here on you're going to be seeing mostly problems. Make sense so far? Okay, so let's try to play some poker, right? So for those of you who may not know, who may not be familiar with cards, right? The card decks have 52 cards, right? 4 suits and 13 ranks per suit, and the 13 ranks are 2, 3, 4, 5, 6, 7, 8, 9, Jack, Queen, King, and Ace, right? So that's the 13, and Ace is sometimes considered after King, and sometimes it is considered as 1, right? So that's but in this problem, these details don't matter. All that you're working with is that there are 4 suits and 13 ranks, right? So the question is, suppose you have think of a random poker hand which has 5 cards. So basically each poker hand is a 5 element subset of these 52 element set, okay? And you are being asked, okay, what are the number of those 5 card hands that have all 4 suits of the same rank? Okay, so for instance, 8 of spades, 8 of diamonds, 8 of hearts, and 8 of clubs, right? And then the 5th card doesn't really matter what it is, right? So the only thing that we care about are the 4, right? So all these, okay. Now here in this case, doesn't matter how whether they occur together or whatever, but because we treat the hand as a set, right? So the order in which they appear doesn't matter. So how can we count this number?
Professor?
Yeah.
You forgot to count 10.
Oh, I did. Okay, yeah. Okay, thanks. So how many such cards, card hands exist? How do we go about counting this?
Would it be to first satisfy the condition? So like 13 for one of the suits, 13 for another suit, 13 for the third suit, and times 13 for the fourth suit. And then for the last card, just pick any of the other 48 cards.
Okay, so again, the condition is that this is 8, 8, 8, 8, 2, 2, 2, 2, right?
I misunderstood the condition.
Right, so the 4 have to be exactly the same number, right? And the fifth one can be anything. Okay, so
Okay.
So how would we do this? This is not a very difficult problem. So if you thought I was giving, springing a really complicated question at you, that's not the case. So you can try. Greg?
Then maybe 13 times 48.
So you want to explain?
Yeah, with the idea with 13 times 48 is you have 13 choices for the ranks that exist. I mean, 13 choices for 13 choices for a rank.
For
and
the
you know
one
they're
that
gonna have the
repeats,
same suit.
right? So for the car, for the rank that repeats, you have 13 choices.
Yeah.
Right. And then for the last card,
you have any of the other 48 choices.
right? Because you have already picked 4 cards. So out of the 52, you have exhausted 4, right? So therefore, there are 48 left. So the number is going to be 13 times 48, which is 624, right? So this is nice, not that difficult. Okay, so so if you think about what is the probability of getting such a hand, well, it's not very large because the number of possible, if you consider the total possible 5 card hands, that is 52 choose 5, which is a pretty large number. So in contrast, this is a pretty small number. So the possibility of getting this is quite small. So if this is if this is a good hand, then and you get it, then you know that it is you are really lucky. So another example based on poker is a full house is a hand with 3 cards of one rank and 2 of another rank, right? So so let us say that one example is 8 of spades, 8 of diamonds, 8 of clubs, and 7 of clubs and 7 of diamonds, let's say. So this is a full house, right? So 3 cards of one rank and 2 of another, right? And of course, you could have had 8 of spades, 8 of hearts, and 8 of clubs, and 6 of spades and 6 of hearts, and that's also a full house, right? So so essentially you need to have you pick the rank for the one that's appearing 3 times, the rank for the one that's appearing twice, and and then you go from there. So notice that it says 3 plus 2, right? It's not that, oh, the fourth one could also be the same as the first one, right? So you need to have something that repeats 3 times and another that repeats 2 times. And this requirement makes the problem somewhat easier to solve than other problems that we will encounter later on in this lecture. So how would we go about counting this? Somebody else wants to try?
Is it just 13 times 12?
Why don't you go ahead and explain to me, because
Okay.
yeah.
So it says 3 cards of one rank, so it could be any of the 13, and then 2 of another, so it's any card except the other one, except the rank of the other ones.
Let's stay with the first part, right? So you're choosing 3 of one type, right?
Yeah.
But just as I showed here, there are 2 different ways of picking the 8, right?
Yep.
Because there are 4 suits, and you have to pick some of those, 3 of those, right?
Mhm.
So what is the number for that? So that is, so you choose the rank in 13 ways, and then you can choose
Is it
of the 4 suits, you can choose which one to leave out, right? So you pick the other 3. So this part can be chosen in 13 times 4 ways, correct? Right, because you're first choosing the rank, and then you're choosing the suit of the 3 cards, right? And again, instead of trying to, so there are 13 ranks, and you're choosing 1, right? So that's how we get the 13. And then we have 4 suits, out of which you are choosing 3. And that's the same as this, right? So I'm sure most of you have come across this identity, right? N choose k is the same as n choose n minus k, right? You can think about why that is, but that's an identity that's so instead of doing 4 choose 3, we can do 4 choose 1, which is 4, right? So now we have different ways of figuring this. And then what will be the expression for this? Someone else wants to try? This should be easier than this, right? Or at least no different, right?
For the 2 of the another rank, would it be 12 times 4 choose 2? So 12 times 6?
Right. Right. So again, you have to choose the rank of the 2, right? And you no longer have 13 available, because 1 has already been chosen here. So you have only 12 ranks available. So you have to choose one of those 12, and then you get to choose the suit of the 2 cards. So there are again 4 suits available, and then you have to choose 2 of those, right? So the number is that, right? So 13 times 4 times 12 times 6. So you have somewhat larger number of full houses as 4 of a kind, right? 4 of a kind was 600. Full house is y. Okay, yeah, full house is it's about 6 times, right? So
could you explain how 4 choose 2 becomes 6?
right, so what is the
Okay.
it's 4 factorial by 4 minus 2 factorial 2 factorial, right? So that's the definition of 4 choose 2,
Okay.
right? So if you do the math, it'll be 4 6. Yeah. So again, you don't have to worry, right? Because you have to give just what the formula is. But also, when you do these problems more, you will start remembering what these certain results are. Like 4 choose 2 is something that you'll see so often, and you'll remember that it is 4 choose 2 is 6. Okay, suppose you have another problem, right? This hand is probably not worth anything, but still it's useful to, as a counting problem. This is no different from any of the other counting problems that we have looked at, right? So suppose you want a hand in which no rank repeats, right? So how many possible ways are there? Somebody wants to, you can raise your hand and answer. See, you can pick the easier problems now and then feel that you did answer some question already, or pick a problem later that's, could be harder. Okay, Owen?
Well, for the first card, there are 13 ranks it could be.
Okay.
And then for any of those ranks, there would be 4 different cards to choose from.
Suits, yeah.
And then for the next card, it'll be 12 times 4. And then 11 times 4, 10 times 4, 9 times 4.
Okay. So good. So so we can do this in 2 steps. So you are picking the rank and the suit, one after the other, but obviously it doesn't matter. We can pick all the ranks and then pick all the suits. So the thing to remember is that if you just start multiplying, then you will end up double counting, right? So you need to be careful about that, right? So so you need to make sure that the first one is posed as a subset problem, because it's not going to matter the order in which you pick them, right? So the order of the cards don't matter, right? We treat the hand as a set. Okay, so that's why we need to think about it, the first step, as choosing the 5 ranks, a subset of 5 among 13 possible ranks, right? So once we have done that, then we can choose the suits, and now those choices of suits are actually independent, right? It's not because suppose you have you have chosen the ranks as ace, 3, 7, 9, and jack, right? Now you can see, you can then easily see that the way I choose the suit of A is completely independent from the way I choose the suit of 9, right? And therefore I can simply, there are 4 ways of choosing this, 4 ways of doing this, right? And all of these choices are independent. Therefore, I get to that 4. I am going to do that, right? Multiply that, and that is 4 to the power 5. And then, so the first step gives me 13 choose 5. The second step gives me 4 to the power 5. And so you end up with quite a large number, right? So if you recall the total number of possible poker hands, does anyone remember what it was? Approximately? I'm surprised, the class of 55, nobody remembers that one number. Okay, that's so it was about 2.5 million, right? So of course I remember because I typed it in into the slides, right? So so maybe I overestimate the likelihood of someone remembering it. So so you can see that about half of the poker hands don't contain repeating ranks. So if you get dealt a hand in which nothing repeats, don't think it's unusual, right? with about a 50% probability, you can expect a hand like this. So, so to see why, what was, wrong in the initial answer that was given, just take this, right? So you could have, chosen, ace and 3 and 7, 9, jack, or you could have chosen 3 and then ace and 7, 9, jack. So there are just so many different orders in which your choices could have appeared. And so when you say I can choose the first rank in 13 ways, the second rank in 12 ways, then you are going to end up with all these duplicates, right? Which is why we need to divide this by an additional 5 factorial, which is reflected when you do the 13 choose 5, right? So always remember that when you are when you're counting sets, you need to take into account that you should not repeat the same set simply because the elements appear in different orders, right? So you need to be careful about that. Other than that, this is not a difficult problem. But again, as we go, the problem will get, so the actual probability happens to be 0.5071. Okay, so now this one gets, slightly a bit more complex than the previous one. So now we are looking for 2 pairs, right? So 2 cards of one rank, another 2 cards of a different rank, and then the 5th card doesn't matter. Okay. So how could we solve this? Okay, so obviously we want to figure out how many ways we can choose the first pair, then the second pair, and then the 5th card, right? So how would we do that? Someone? Kelly.
I'm not quite sure how to do it with like choosing and stuff, but I think the basic idea would be like the first one would be 13, like the first card would be 13 times 4. And then the second one would be like 13 times 3 because you would have 3 options, like 3 other
So
cards left.
you're going through the steps. If you just if you don't rush through the steps, you will get everything right. So there are 13 ways to choose the rank here, right? And then you need to choose the suit, right? So how many ways are there?
4.
It's 4, choose 2, right?
Mhm.
Okay, because there are 4 possible suits and you have 2 cards that you're choosing, right? So you need to choose which subset of these 2 suits are, which subset of these 4 suits is going to be on each of the cards that you chose, right? So it's 4, choose 2, and then the next part.
So then the next part would be 12 times 4, choose 2.
So let me be more, let's just always write down just the expressions, right? So 13, choose 1, and 4, choose 2. And then, no, this you said is 12, right? Okay, that's correct, 12. 12, choose 1, because obviously we already chose a rank. So we need to choose a different rank, right? It is very clear that you have to choose a different rank. It doesn't say, you can choose the same rank, because that would be 4 of a kind. And what about choosing the suit?
So it would also be 4, choose 2.
Right. Okay. And then what about the 5th card?
for the fifth card, you would choose 48, choose 1.
Okay, so so this is following pretty much what we have done in the some of the previous problems. But as I said, this problem is a little bit more tricky. And can you tell me where? Can someone guess where the problem could be? Right, we are kind of more or less there, but there is some. It's not entirely correct. Samuel, do you mean to have your hand up, or you forgot to put it down? Okay, so Brian.
I think it's 44 instead of 48 because if it was of the same rank as one of those other two, then that would be 3 of the same rank.
So your theory is that it shouldn't be one of these 2 ranks. But
Yeah.
at least the way the problem is written, I don't think that's a constraint.
Oh, okay.
Okay, I may find out on the next page that it is a constraint, but I at least what is on this slide doesn't tell me that the 5th one there is any constraint. But there is still a problem. Is it Owen? You want to try again?
Yeah, instead of doing 13 choose 1 times 12 choose 1 for the 2 ranks, it should be 13 choose 2 because the order that you choose them in doesn't matter.
Okay. Okay. Any other problems? Okay, so the difficulty is that the 5th card you choose, right? If it happens to be, so let's say, let's consider an example, right? Let's say, 9 spades, 9 clubs, right? And then let's say we choose, 7 hearts and 7, spades. Okay, and let's say the 5th card happens to be 7 hearts, right? Now you can see that you have these 2 cards here, right? I'm sorry, I don't know why I'm saying 7 hearts. Obviously, that's not 7 hearts. Seven diamonds. Okay, so now you can see that you can arrive at this way, or you could have said, 9 spades, 9 of clubs, 7 of diamonds, 7 of spades, and 7 of hearts here, right? So, so the difference being that this is the 5th card, right? And this is the 2nd pair, this is the 1st pair, right? But obviously these 2 hands are the same, right? So what this means is that there are going to be situations where we end up double counting. Okay, so that's what we need to okay, so So I did so as I said, when I go to the next slide, I might find out that there is the additional condition, and it is not an arbitrary fifth card. It is different from other two. Okay, so so the double counting is therefore just the first thing that that was pointed out. That is, we don't care which one is the first and second here, right? So obviously we could have flipped these two, right? And therefore, either we could have taken this as 13 choose 2, right? Or we could have gone through the same calculation as we did, right? And then realize that we are double counting everything because whatever we think of as the first pair could be counted as the second pair, and whatever we think of second pair could be counted as the first pair. So this way we are counting everything twice, and therefore we divide that number by 2, right? So so that gives you this number, right? So let's summarize the way we have done this calculation. The way we did this is we picked the first pair, and this is the number we got. We picked the second pair, this is the number we got, and then we picked the fifth card. Okay, now fifth card is 44 because we don't want to choose any of the ranks, right? So if you have chosen 2 ranks here, that eliminates 8 possible cards. So for the fifth card, there are only 44 choices, right? So we pick the first one, the rank and the suit of the first pair, the rank and the suit of the second pair, and the fifth card. And then we multiply all of this. And then we realize that we have double counted because there is no difference between the first pair and the second pair. So we divide by 2, and this is the value you get, right? So we can also do it in a slightly different way, which was, I think, the way that one of the answers suggested was to follow this, which is to first say you pick the rank of the 2 pairs, which can be done in 13 choose 2 ways, right? And then once you pick the rank of the 2 pairs, right? So one of them is going to be, one of the ranks is going to be lower than the other. So you pick the rank, the suit of the lower ranked pair, which is 4 choose 2, and then you pick the suit of the higher ranked pair, and obviously these 2 are independent, and this step, this choice is independent from this choice, it's independent from this. So you can multiply all of that, and then you have the last card, which can be whose rank can be chosen in 11 ways, and suit can be chosen in 4 ways. So we get this formula, and of course the 2 should match, and they do, right? They are not even that different, right? They are very close, right? So we are because all we are doing here is we are trying to pretend that the first pair and second pair are distinguishable, and then we are saying no, they are not distinguishable. So we're going to divide by 2. Here we are starting out by saying that we can't distinguish between the 2 pairs, right? So it's not even a particularly different way of doing it, but still, it's always helpful to work out the problem in more than one way, and verify that the answer matches. So why don't we take a break here? I will restart back at 4:40. Okay, so we'll start at 4:40 and then go on for another hour or so. Okay.
Are we staying in this call or switching over to our TAs?
No, we are. I'm coming back.
Okay.
Okay, so so to make that easy, I'm just going to pause and not even stop the session. Okay. Okay. So does anyone want to try? What is the how can we count this? Right. So you want to have all 4 suits in your hand. Yes? Anybody? No?
Would it be 13 times 13 times 13 times 13 times 48?
The explanation being, well, you can, you know that this all 4 suits have to be there. So you don't need to, there is no choice of the suit itself because all 4 have to be there among the first 4 cards. So you have 13 choices for the rank of the first suit, 13 choices for the rank of the second suit, and so on, right? And then the 5th card is chosen in one of 48 ways, right? But as I said, it's not entirely independent. So where could we be double counting? Okay, so let's take an example, right? So let's say 4 of spades, 5 of diamonds, 7 of hearts, and jack of clubs, right? And then the 5th card could be, let's say, queen of diamonds. Okay, so can you see where things could be a double counted? Again, you don't have to be sure, but you can guess.
The diamonds are, since order doesn't matter, the diamonds are counted twice.
Right, so the 5th one obviously must have the same suit as one of the other 4, right? And so among the 2 that have the same suit, you can't tell whether it is whether that particular card should be considered part of the first 4 or should it be the last card, right? Because we could, the way we are generating this, we would generate this same hand in right? So we would generate the same hand twice. Again, viewed as a set, the 2 sets are identical. But if you make this distinction between the first 4 and the last one, looks like the 2 are different, right? So we are double counting, and we can say that it is only double counting because there is going to be only 2 cards that have the same suit, right? So the confusion is only between the cards that have the same suit. So as a result, we can say for sure that each of them is going to be counted exactly twice, not more than twice. So all we do is we take the formula that we had so far, 13 times, 13 raised to the power 4 multiplied by 48, and we divide by 2 to account for this double counting of the last card with the other card in the 5 set hand that has the same suit, right? So, and then you divide by 2, and the result is this number. So once again, this is not a very unusual hand. The probability of this, comes out to be about 0.25, right? So the total number was like 2.4 something, 2.5 million, and so this is about a quarter of that. So let's take one last example before we, say we are done with poker hands, right? So let's say you want at least 4 distinct ranks. Okay, so sometimes you have a problem where it's not immediately obvious how to solve the problem directly, and in those cases we may need to break them down into disjoint subcases. Okay, so so for instance, if you say at least 4 ranks, right, then we can divide that into exactly 4 ranks and exactly 5 ranks, right? So we can't have more than 5 ranks because we have only 5 cards in our hand, right? So the only 2 possibilities are we have 4 ranks and we have 5 ranks, and we already calculated this before, right? So no 2 cards are the same rank. We did this calculation before, and we got that. So now we only need to calculate, how do we get exactly 4 ranks, right? 4 distinct ranks. So what would be the formula for that? How would we calculate exactly 4 ranks? Anybody else wants to try? I know this is a long class, but at the same time, if I just keep repeating this, it's not going to help anybody. Because if you just want me to repeat, I can just post it on the website. And so Greg, go ahead, please.
13 times 13 times 13 times 13 times 16 divided by 2.
And then what?
Multiplied by 16. The reason I chose 16 was there's a force. We
So we're talking about
like,
this problem, right? 4 ranks.
Yeah.
So I don't know how
or
you...
12, I think. With the assumption that we want to choose one more card that's already within one of the ranks we chose. There's 4
again,
ranks, I guess. 3.
Let us.
So 12.
I think maybe there's some confusion on terminology that I thought maybe is not there. So there are 4 suits and 13 ranks.
Right.
Right. So if I said I want 4 ranks, 4 different ranks, how will it be 13 times 13? Because once you choose a rank, then that rank is not available anymore.
Oh, right. Sorry. 13 times 13 times 12 times.
Okay.
Well,
because sometimes I can't, because you're telling me a number, I can't really.
Right.
I have to try to read what is in your mind based on the number. That's why I'm asking you that question. Okay. So, and then what was the last one, please?
And then for the last one, I think it was times 12, since for each of the ranks we chose, there's three other suites, and we also multiply by 4 to the 4th.
Okay, so the point is that the 5th one, because we have exactly 4 ranks, the 5th one is going to have one of these ranks, right?
Yeah.
So it's 4 choose 1 in terms of the rank, right? And what about the suit? You already have the same rank, which means that one of those suits is gone. So it's, I think this is what you're referring to when you said
Yeah.
12, right? So let's, okay. So this expression, right, says it's not counting a set, right? It's counting like a permutation.
Yeah.
Right? So we need to say that we are choosing the 4 ranks. So instead of this number, right, we should say
Divided by 4 factorial.
yeah, but obviously, you know, we could
13 choose 4.
yeah, right. We could say 13 choose 4 to choose these ranks, right? And then we have to choose the suits for each of them that we haven't done, right? So that'll give us, because each of their suits can be chosen independently, right? So each of them have 4 different possibilities. And so you'll get 4 times 4 times 4 times 4. So that'll give you 4 to the power 4. And then 4, 1, 3, 1. Okay, so let's see what the answer is. Okay, so so you can choose the ranks in 13 choose 4 ways. And then there are 4 ways to choose which rank is repeating. And okay, so the calculation that we have in the previous thing has, let me write it down here. So you'll see where the difference is and therefore, you know, where the mistake was made, right? So we said 13 choose 4 times 4 to the power 4 times 4, 1 and 3, 1, right? So whereas the expression that we have here is 13 choose 4 times 4 to the power 3 times okay, so let me just simplify this, right? So there is a so 4 and 4 to the power 3. So we still have 4 to the power 4, and then we have 4 choose 2, right? So here, that is the difference, right? So so the point, the thing that you always have to be careful is, of course, duplication. So what is the duplication that's happening here? Yeah, go ahead, Greg. You're muted.
The duplication is that the last card could have could have the same suit as one of the previous cards.
Right. So so the problem is that we can't really distinguish between the last card, whether it is the last card or one of the first 4, right? It's the same problem that we had before, right? So we mentally make this distinction between the first 4 and then the last one, right? But really, when you think about it as a set, the distinction is not there. So we need to be careful and make sure that we are not double counting something, because first time we count something as part of the fifth card, and the other time we count it as part of the first 4, right? So that's where you know, you have to either start from this and account for the double counting and then divide by 2, or simply say that simply treat the problem of choosing the suit of the non-repeating rank separately from the suit of the repeating rank. Okay, and so once you do that, then you get rid of that duplication, and then you get this number, which is very large, right? So so what it says is that at least 4 ranks is actually very, very high likelihood, right? So you're probably going to you're probably going to always have a hand which is has at least 4 ranks. Okay, so so the one of the mistakes, most common mistakes, is not recognizing that you're going to you end up counting something twice, right? So so that's the one that you need to watch out. And with as you do more problems and get more practice, you will get better at recognizing when things are repeating. Okay, so let's switch and talk about a couple of principles, and then come back to the problems again. So there is a principle called Pigeonhole principle, which is so obvious that one would wonder why we talk about it in the class. But let's start by asking, posing this puzzle, which many of you may have, or some of you may have seen already, right? So you have a drawer in a dark room, has 3 types of socks, right? So it's dark, there's no light. So obviously you want to get a pair, but you can't check when you're pulling the drawer, the socks out of the drawer. You cannot figure out whether they match or not, right? But what you want to do is you want to pull out enough of them that when you go to the light and see, there is likely to be at least 1 pair, right? So how many do you need to withdraw in order to get a matching pair? Anybody wants to try this? Let's see if we have another person who wants to try. Joseph.
Oh, so I was thinking, so is there, so when it says red socks, green socks, and blue socks,
Yeah.
that means that there's like 2 individual red socks, or like, do we know the exact?
You can assume that it's for all you know, it has an unlimited number of socks in the drawers.
So, well, what I was thinking is, like, I guess, is there, I'm sure there's a way to maybe, I'm not really sure what way you could actually figure out. Well, each sock you pull is unrelated.
So I remember I was in my 7th grade, and someone came and told us this puzzle. And you can imagine that a 7th grade person doesn't know much probability. And of course, whatever probability you're trying to apply that to get an answer out of this. And the instructor tells us, don't think too hard, because this is actually a simple problem. And of course, we can't do anything but think very hard. So Alex?
Well, I mean, if you take out all of them, you're going to guarantee to have a pair.
Yeah, but the problem asks you
minimum number of socks they
yeah,
want?
let's say minimum.
All right.
Or if you're going to make a probabilistic argument, you can say this many you have to draw in order to get at least a certain probability of. So what does the pigeonhole principle say? It just says that if there are more pigeons than the holes they can occupy, then there must be more than one pigeon in a hole, right? That's all it says, right? Something so almost stupidly obvious, right? But such a stupidly obvious principle is actually, very useful. And for instance, it can give you a solution to this problem very easily. Someone else, Andrew.
Is it 4 times? Because assuming you pull 3 and each of the 3 socks are different colors, then the fourth one has to be one of the 3 colors.
Right? So that is the pigeonhole principles, because there are, only 3 holes, right? So red, green, and blue. So if you draw 4 socks, then, and you try to put them into these 3 holes, at least one hole must have 2 socks. So you have your pair, right? So that's the principle. So we can also state the pigeonhole principle in terms of sizes of sets. And so if you have 2 sets, A and B, and the size of the set A is bigger than size of set B, then for every total function from A to B, it must map at least 2 different elements of A to the same element of B, right? Because there is an arrow coming out of every element in A, right? Because that's why it's a total function, right? And these arrows have to go somewhere, and there are not as many elements in B as there are arrows coming out of A, and therefore multiple of these arrows have to end up on the same element, right? So of course, all it says is that just at least 2 of these elements should end up in the same place. So let's ask this question. How many people riding the New York City subway in a day have the same number of hairs on their heads? Some people have their hands raised. Is that because they forgot to put it down, or they want to answer this question? Yeah, so now anybody wants to try answering this question? How would one go about answering this question in a reasonable way? Okay, so what data do you need before you can try to answer this question?
You might need the maximum number of possible hairs.
Okay, so let's say that's 100,000.
What if you look at the minimum? Like, what if they're bold?
Okay, so that's a very, very good question. But we don't want to cheat, so we won't consider that case. So what other data do we need?
The number of people riding in a subway in one day.
Okay, so let's say that's, let's say 100K hairs and 4.3 million, right? So this is the pre-pandemic number, right? 4.3 million people ride the subway in a day. So that tells you what? How many people should have the same number of hairs? So you can tell me on average, right? and then we can see whether.
Would it be 430?
43, right? 1000 K is a million. So 43.
Yes.
So,
that's 43
so
million.
what you can say is that, okay, so at least 43 people will have the same exact number of hairs, right? That you can assert. So the generalized pigeonhole principle says that if the size of set A is greater than k times the size of set B, then every total function needs to map at least k plus 1 different elements to an element of B, right? And this is the version that we just used to say that somebody should have at least 43, that at least 43 people should have the exact same number of hairs, which of course, if you think about it, it seems so, without going through this process, if someone just asks you, what is the likelihood, you would probably say, well, it's very unlikely, right? The people having the exact same number of hairs. Okay, so let's ask another problem, right? So we know that COVID has killed a lot of people in the world, right? So I think it's about 1.1 or 1.2 million people that are dead because of COVID, right? So that seems like a very large number. But we want to understand the context, right? So we want to understand, for instance, how many people, say die of natural causes, say in 6 months, right? So how would we go about answering that? Anybody wants to try? How many people in the world die of natural causes every, say, 6 months, which is roughly the time the pandemic has been with us? So what data do we need in order to answer this question? So it's obviously like a subway, and number of hairs question, right? So you need some data to answer this question. What is the data that you need? Other than, how many people actually die, every day or every 6 months, right? So that's what other data from which you can estimate this.
Would you need the total amount of people living?
Okay, so what is the population of the world? I think at least some of you should know that number, right? Again, rough, we don't want, 7-digit accuracy, just,
7 billion?
So 7 billion, right? So that's, yeah, if you ask me, that's what I would say. I don't know whether it's, I know it used to be 6 billion at some point. I don't know whether it has reached 7 billion, but maybe it has. So 7 billion, and then what else do we need to know? What other piece of data will help us estimate how many people die in a year?
So I mean, what I'm confused about here is, wouldn't we need the data of, like, let's say how many people died to heart attacks? But that'd be a rough number, right? Or is it more so percentages we're looking for?
No, I'm trying to find out how many people die of natural causes in a day or in 6 months in this case, right? Or a year, right? So if you have the information for a year, then we can divide it by 2 and say in 6 months. So we know that the population is 7 billion, that somehow, obviously, the higher the population, the more the number of people that die, every day. So what other information could we need in order to make an estimate?
Would you use the the average lifetime of a person?
And what would that be? What is the life expectancy?
Like 80 years?
It's,
I'm not
I guess
sure.
even in the US, it's only 78, right?
Yeah.
So I think in the more populous countries, I think it's quite a bit smaller, but it doesn't really matter. Let's say 70, right? So given that, from this 2 pieces of data, what can we say about the number of people that die every year?
I guess it's all the people who turned 70 that year, but I'm not sure
That
what
will be?
I'm not sure what percent of the 7 billion that would be.
Well, again, yeah, right. So
It's not
these
about
are all,
percentage,
rough guesses, right? So we are going to be right within a factor of 2 or 3, but not, any more accurate, because we are just trying to, make educated guesses about this, right?
Right.
So if that is the kind of number we are looking at, then how would we take these 2 numbers and turn it into the number of people that die in a year?
Would it be 100 million die?
Right. So we would just say that, okay, let's just assume that, the people have the same, the distribution of ages is uniform, right? Roughly uniform, right? We know that it is not uniform. We know that there are, especially again, the very populous countries, generally the population tends to be much younger. So the number of older people is certainly smaller that way. But let's, but I don't think it's skewed by more than a factor of 2 or 3, right? So it's reasonable to say that the ages are uniform, and therefore, if there are 7 billion people, there will be 1/70th of that will be in the last year of their life, and therefore they will likely die. And so the number would be like right, 100 million people die each year, right? So so that tells you that this number is, while it makes a significant difference to the 100 million, it is not something that is going to it's not something that increases the death rate so much that it's not making it's basically still only a 1.2% of the number. Not to say that that's because nobody wants anyone to die. So obviously these are all it is terrible that so many people die, but at the same time knowing that this is the number to compare gives you some way to at least have a context and have a way to interpret this number in light of that number. Okay. So let's ask another question, right? So let's take 100 random numbers with 25 digits, right? So I'm using 25 digits because if you add up these numbers, right? So there are so many different digits that if you add up 2 sets of these 25-digit numbers, you would expect that they are unlikely to have the same value. Okay, so but let's try to answer this question. What is the So once again, it seems that if you add two different subsets of 25-digit numbers, they are unlikely to add up to the same value because, well, there are so many different digits. How are we going to, right? I mean, we are not choosing these numbers so that they add up, right? These are just completely random 25-digit numbers, right? So the chances that when you add them up, they will produce, any particular value is so infinitesimally small, right? Okay, so now how can we estimate the likelihood, or rather than likelihood, the possibility that two subsets of 25-digit numbers will add up to the same value? Okay, so we have 100 random numbers, right? So we are going to take subsets of these 100 random numbers, right? And then see if there are two subsets that add up to the same value, right? So how can we answer this question? Is it likely, possible?
Well, it's definitely possible because you can just have.
Right, it is definitely possible,
Yeah.
yes. So let's say likely. Or is it a certainty?
When you say adding up, do you mean taking each individual digit and then combining, as
No, adding 25-digit numbers, just they are integers, right?
Oh, okay. I see.
Yeah.
So you say, all right.
Yeah, they are integers, you just add them up.
Well, if you're adding like up to 125-digit integers, it wouldn't be able to have any more than like 28 digits for the sum. So there would be like 10 to the 28 possible sums. But since there are 100 integers, you have 2 to the 100 possible subsets.
Okay, so let's do this slowly, right? So when you add 100 of these numbers, so 25-digit numbers means 10 to the power 25 possible values, right? And if you add 100 of them, so your result is going to be a 27-digit number. So it's going to be 10 to the power 27 possible, numbers. 10 to the power 27 possible sums, right? So these the point is that the sum cannot be more than this, right? So there are only 10 to the power 27 distinct sums that are possible because, you have only, when you add up 100 numbers, you're going to have a 27-digit number, and a 27-digit number can only represent 10 to the power 27 possibilities, right? So the result of adding any subset of numbers, the result is going to be within 10 to the power 27, right? Now, how many subsets are there? So there are 100 elements. So how many subsets are there? Somebody
2 to
already
the
said the
100.
answer, right? It's 2 to the power 100, right? It's a power set problem, right? So 2 to the power 100, if there are 100 numbers, then the number of subsets is 2 to the power 100. So how does 2 to the power 100 compare with 10 to the power 27?
2 to the 100 is larger.
So how do you compare? Yeah, I mean, you're right, it is larger, but why? Anyway, so, unfortunately, so actually log of 2 to base 10 is something like that, right? So somebody like me will know, because when I was young, there were no calculators to use, right? So we needed to remember the way we would do multiplication is you look up the tables for the logarithm of numbers, and then when you come across some numbers, very often you remember forever what the logarithm is. So which means that 2 to the power 100 has a logarithm of 30 point, right? 2 to the power 100 will have, you just have to multiply the log by 100. So that'll give you 30.10, which means that the number is something like 10 to the power 30, right? So there are 10 to the power 30 subsets, but the sums, there can be only 10 to the power 27. And therefore, the Pigeonhole principle tells you that there are many subsets that must have the same sum, right? It tells you that there are at least 1,000 subsets that will sum to the same value, right? So yeah, so it's not only you can say more than, okay, there are repetitions. What you're saying is that it's going to repeat 1,000 times at a minimum, right? So that's again something that, so the power of Pigeonhole principle, there are two things that it gives you. One is that when faced with problems where you in the beginning don't seem to have a way to answer the question being posed, it gives you a powerful way to answer those questions, and come up with these sorts of arguments. So let's so the next thing that I want to talk about is essentially the last topic in counting, and that is called the inclusion. The inclusion-exclusion principle. So, so far, we talked about counting in the context of disjoint sets. And there we just said that if you want to count the size of the union of two disjoint sets, then all you do is you simply add up the sizes of the sets, right? So what happens when the sizes, when the sets overlap, right? So this is one of the problems that you have solved many times in high school, right? So you are given all these Venn diagrams of set S1, set S2, and you're often told that, okay, S1 has 25 elements, and S2 has 50 elements, and S1 union S2 has 60 elements or something like that. And then you are asked, what is the size of S1 intersection S2, right? So this is a common problem that you come across, right? So the inclusion-exclusion principle is simply a manifestation of this sort of reasoning, which basically says that to find this intersection, what you want to do is you are going to, the reason why S1 union S2 is less than the sum of the sizes is because anything in the intersection gets double counted, right? So it's going to be counted once on behalf of S1 and once on behalf of S2. If you simply add up the numbers, then you'll get 75, and there is double counting there because something gets counted once on behalf of S1 and again on behalf of S2. Now, if you're given the total size as 60, then you know that this is 15, right? So this is 10, right? So this is the way you solve this problem. And basically what you can say is that the size of S1 union S2 equals the size of S1 plus the size of S2, and then minus the size of S1 intersection S2, right? Because the intersection, we will be counting those elements twice if you just simply add up the numbers, right? So for union of overlapping sets, right? So if you have two sets that overlap, then the inclusion-exclusion principle simply says, the size of S1 union S2 is going to be a bit more complicated than the disjoint case. And the complication is that you have to subtract the intersection, right? So obviously, this is a special case of this, because in the disjoint case, S1 intersection S2 is empty. Therefore, this is 0. So you have S1 union S2. The size of S1 union S2 simply becomes S1 plus S2. Okay, so now, so the union of two sets, the principle simply says this. Okay, so now let's see the union of three sets, right? S1. Okay, so how would we go about calculating, right? So clearly, that part is, if you simply add then you can see that all the the shaded regions get counted at least twice, and this region in the middle, right, seems to be getting counted multiple times. So what do we do? So we want to get rid of the double counting. So what should we subtract from this? Greg?
We can subtract S1 and S2 and S2 and S3 and S1 and S3.
Right, so all the shaded regions have to be subtracted, right?
Right. And then also add back in the last section.
Okay, so now what have we done? So if you look at what is inside here, right? The middle, so that was triple counted here. It was counted in S1, it was counted in S2, it was counted in S3, right? So now we also triple subtracted it because it got subtracted out as part of S1 intersection S2. It got subtracted out of S2 intersection S3. It got subtracted out of S1 intersection S3. So now it was triple counted, and then we, reversed all of the triple counting. So now we have counted those elements exactly 0 times, right? So we have to add that back. So that is the inclusion-exclusion principle for 3 sets. Okay, so now, so that's what this thing says. So let's, try to solve a couple of problems using this principle and then wrap up. Okay. How many permutations of these numbers contain a 42, 04, or 60? Okay, so how can we approach this problem? So it's an application of inclusion-exclusion principle, but let's not worry about it for the moment, right? So let's first say, how do we count permutations that contain a 42? Right, so what are the permutations? How many permutations of digits 0 through 9 exist that contain a 42? So how can we go about answering this question?
Are we setting a length to the number?
Okay, so it's a permutation of a set, meaning that.
Oh, okay, gotcha. Okay.
So you have 10 digits, right?
Right.
Because there are 10 numbers here, so 10 digits. Yes. Is there anybody other than Greg who wants to answer this question? Okay. So the way you do that is, fairly simple. You say, okay, so I'm going to, if it has to contain a 42, then I'm going to kind of fuse 4 and 2 together, right? And I'm going to consider it as if it's a single digit, right? So the rest of the digits can go anywhere, but 4 and 2 need to occur together. So instead of thinking about 10 digits, I'm going to think about just 9 digits because I have kind of glued together 4 and 2, right? Now I can think about the permutations of these 9 numbers. So that'll give me a 9 factorial for the sets for the permutations that contain a 42. So similarly, I can say, this is 9 factorial, this is 9 factorial, and this is 9 factorial, right? So, but what I'm asking for is something that contains, at least one of this, right? So if I said, S1 here is permutations containing 42. So let me just call it S42, right? S42 is 9 factorial. S04 is 9 factorial, and S60 is also 9 factorial, right? So if I want at least one of these, that means I'm looking for the set right? Because this set includes everything that contains a 42. This one contains everything that contains a 04. This set includes everything that contains a 60. Therefore, if I take the union of these sets, that should be what I'm interested in, right? So I need to compute the union of these 3. And so I need to apply my inclusion-exclusion principle, right? Because these obviously among the permutations that contain 42 there could be a 04 in there, right? We are not saying that there won't be a 04. Similarly, there could be a 60, right? So these are not disjoint sets, so we cannot simply add them up. So we need to apply the inclusion-exclusion principle. And therefore, we also need to know what is the size of, what is the set 4204 that contains all of this, and 0460 and 4260. So how would we calculate the number of sets that contain both a 42 and a 04? Greg?
We can do the same thing and glue them together. So you have a 0, 4, 2, and that would just make it 8 factorial instead.
Right. So we glue 4 and 2 together, which means that we lose one element out of the 10. We glue 0 and 4 together. So that takes out another element. So now we have only 8 things to play with. So this is going to be 8 factorial, right? And the reasoning is the same. So all of these will have 8 factorial. And finally, for applying the inclusion-exclusion principle, we need the S420460, which is going to be 7 factorial, right? Because we are going to again glue one more, which takes out one more digit. So the final answer is 3 times 9 factorial for adding up the sizes of each of these sets, minus 3 times 8 factorial for taking out these, and then adding back the 7 factorial, right? So this is what we do. And so that is the final answer. Okay. So I think we can stop here. If you have any questions, go ahead and ask. Otherwise, you can drop out. So I'm going to post a poll on Piazza. So when it is posted, please answer it. Right? I want everybody to answer the poll. Right? So vote in the poll, and then that'll help me decide about some extra help sessions. Okay. Very good. Any other questions? Yeah, otherwise feel free to hang up. Enjoy the rest of your evening.